Welcome to Ask and Learn.
We are given a deterministic finite-state automaton, and we are asked to find the language recognized by this automaton. This automaton is the one in problem 20 from the book. So we see that the figure contains 4 states, S0, S1, S2, and S3. I'll construct a table. So in the left column, I'll list the different states. In the right column, I'll have the inputs, which can only be 0 and 1. And if there's an arrow in the diagram from Si to Sj with a label of x, then I'll write down Sj in the row Si and in the column x of the table. So for example, we see there's an arrow from state S0 to S1 with a label of 0. So in the table, I'll write S1 in the row S0 under the column 0. Likewise, I'll complete the rest of the table. We see in the diagram that S0 is marked as the start state. And we also see from the table that only S1 and S3 are circled twice, so they are the final states. So this means that a string will be recognized by the automaton if we end at state S1 or at state S3. So let's break this down into cases. Suppose the string starts with a 0. Well, in this case, from our table, we see that we move from S0 to S1. And then we see that we remain at state S1 if the remaining string contains only zeros. Now, suppose that instead the remaining string contains at least 1, 1, then the input table tells us we're moving from state S1 to S2, and we see that in state S2, if we move to state S2, then we have to move to state S3, and once we're in state S3, we're stuck in state S3. Before we do that, first I'll add these strings. So it follows that all strings consisting of only zeros and at least 1 0 are in the language. So we have the concatenation of set containing 0 and the clean closure of the set containing 0 is a subset of the recognized language. Now, for another case, let's suppose the string starts with a 1. Then the table tells us that we remain at state S0. And in fact, we're going to remain at S0 until first 0. So suppose that remaining string has a 0, then we're going to move from state S0 to S1, just as in the previous case. And again, we see that if we suppose that the remaining string contains only zeros, then we're going to remain at S1. And so it follows that all strings consisting of only ones followed by at least one zero are in the recognized language. So in other words, strings of the form concatenation of set containing 1 and the clean closure of the set containing 1 and the set containing 0 and the clean closure of the set containing 0 is a subset of the recognized language. However, suppose that we obtain a 1 after the 0 is required to end up at state 1. Then it follows that we move from state S1 to S2. And we see that at S2, then suppose that the remaining string has at least one bit. Then, no matter what, we're going to be moving from S2 to S3, which is a final state. And we see that in S3, we're always going to remain at S3. So it follows that the sets of the strings ending at state 1 followed by a 1 and at least one other bit are also in the recognized language. So for example, we have the concatenation of the set containing 0, the clean closure of the set containing 0, the set containing 1, the clean closure of the set containing 1. The set containing 0 or 1. My mistake. And the clean closure of the set containing 0 or 1 is a subset of the recognized language. And likewise, well, we can actually abbreviate this by performing one of the concatenations as concatenation of the set containing 0, clean closure of the set containing 0, and the set containing 1, 0, 1, 1, and the set clean closure of set containing 0 and 1 is a subset of the language. We also have that the concatenation of the set containing 1 and the clean closure of the set containing 1 and the set containing 0 and the clean closure of the set containing 0 and the set containing 1 and the set containing 0 and 1 and the clean closure of the set containing 0 and 1. Well, this is also in the recognized language, and in fact this can be abbreviated by concatenating to the concatenation of the set containing 1 and the clean closure of the set containing 1, set containing 0 and the clean closure of the set containing 0, and the set containing 1, 0 and 1, 1, and the clean closure of the set containing 0, 1. And so we see that the language generated by the machine is going to be the union of all these sets, since we've covered all our cases. So we have that this language LM is equal to, we have 0, 0 star union 1, 1 star, easy way to write this. Yes, we have 0, 0 star, union with 1, 1 star, it's actually 1, 1 star, and then 0, 0 star. That's how we get back to S1. Then union with 0, 0 star, 1, 0, 1, 1, 0, 1 star, union with 1, 1 star, 0, 0 star, one, 0, 1, 1, 0, 1 star, and we see that we can write this as, in parentheses, 0, 0 star union with 1, 1 star, 0, 0 star, so essentially we can group these. So I'll group them like this. I'll group these first two together and the last two together as well. And we see that the first two can be combined to give us 1 star 0, 0 star, and then union with, and then the other two sets can be combined to give us 1 star, 0, 0 star, and then next to that we have 1, 0, 1, 1, 0, 1 star, so our answer is 1 star, 0, 0 star, union with 1 star, 0, 0 star, 1, 0, 1, 1, 0, 1 star.